Alright, here is one of my free assessments. This assessment focuses on Chapter 21, the Lorentz Force, to be more specific. In previous chapters we used the electric force to find the net force on a point charge due to electric field, and we used the magnetic force to find the net force on a point charge due to a magnetic field. Now we're going to combine the two forces, electric force, magnetic force, to find the overall net force on a point charge due to electric field and magnetic field, and this is called the Lorentz force. The Lorentz force can be defined as the net force acting on an object of charge equals the electric force plus the magnetic force, which is written out right here. And the electric force is equal to the charge times the electric field. So we can say that the electric force is in the same direction as the electric force. And the magnetic force is equal to the charge times the velocity of the object of charge across the magnetic field. And this means that the magnetic force is always perpendicular to the plane that the velocity and magnetic field lies on. And the magnetic force can also be written as charge times velocity times magnetic field times the sine of the angle between the two. And this means that if QV cross B is parallel to each other, then there will be no magnetic force because the angle is 0 and sine of 0 is 0. But by looking at this problem, our angle is going to be 90 degrees, so we can safely say that the magnetic force is actually going to be equal to the charge times the velocity times the magnetic field, which is fully written out right here. So here in this problem, we have a particle with a charge of 9 times 10 to the negative 9th, traveling in a straight line in the negative x direction. It's a constant velocity too, and it's traveling in the negative x direction through an electric field and a magnetic field. The electric field is 3800 volts per meter in the y direction, and the magnetic field is in the positive z direction at 0.4 Tesla. And here I have the electric field, the magnetic field, and the velocity written out in vector form. And by solving this problem, we will be able to show how the velocity of a particle will change the net force on the particle. So since our particle is traveling in a straight line and at a constant velocity, we know that the net force acting on this particle equals 0, so we have that written right here. And we can say that the negative electric force is equal to the magnetic force right here, or the negative charge, the charge times the negative electric field equals the charge times velocity times the magnetic field. And we can cancel out the charge or the Q, and then we can say the negative electric field equals the velocity times the magnetic field. And we can solve for the velocity by dividing the electric field by the magnetic field. By plugging in our values, the velocity of our particle is 9,500 meters per second. Now suppose the velocity of this particle was actually 9,000 meters per second, and the electric field and magnetic field were the same. Would it still be traveling in a straight line? The answer is no, because the magnetic force becomes less than the electric force, causing the particle to have a net force acting on it in the negative y direction, because electric force is stronger. And the same goes for when the electric force is less than the magnetic force, or the particle is moving faster, so in this case, say 10,000 meters per second. And the net force will be acting in the plus y direction because the magnetic force is bigger.